So in this video I'm going to look at carbon-13 NMR. So in the previous video we established that nuclei with odd numbers of nucleons possess a magnetic moment or a property called spin, and they can therefore absorb radio waves, and that flips their spin state round from the low energy spin state into the high energy spin state. So if we had some ethane or chloroethane, then the carbon-13 isotope is 1% abundant. So in a mole of ethane or chloroethane, you would have carbon-13 nuclei present. So you can see I've added the direction of an external magnetic field, and I've put the spin states running in the same direction as the external magnetic field. So carbon-13 NMR only deals with the carbon atoms in the molecules. So what we're looking at is the amount of energy it's going to take to flip these spin states round. And what you can see, hopefully, is that the carbons in ethane are both in the same environment. So if you think about this carbon here, what's it bonded to? It's bonded to 3 hydrogens and a CH3 group. What's this carbon bonded to? 3 hydrogens and a CH3 group. So they are in the same environment. So in ethane, there is one carbon environment, and therefore the amount of energy it's going to take to flip this spin state round will be the same as the amount of energy to flip this spin state round. So how much energy is it going to take? We can see this bottom part of this data sheet is the carbon-13 section. I'll explain the TMS bit in a while. So we are looking at this environment here. So essentially this carbon is just bonded to another carbon, so it will be classed as this environment here. So we would see one peak, because there's only one environment, somewhere in the region between, what's that, just under 10 and about 50 something parts per million are the units, and again I'll explain that later on. So we'd see one peak because there's one environment, and we'll go for, should we go for 20? If we look at chloroethane now, we've actually got 2 environments in chloroethane because this carbon has got a slightly different environment surroundings to this carbon. And again, if you just think, if you can't see that, just ask yourself, well, what's this bonded to? This carbon's bonded to 3 hydrogens and then a carbon with 2 hydrogens and a chlorine on. This carbon is bonded to 2 hydrogens and a chlorine, and then a carbon with 3 hydrogens on, a CH3 group. So we've got 2 environments here, and therefore we will see 2 peaks in the spectrum for chloroethane. So again, if we go to the data sheet, so this environment here, this carbon is a carbon bonded to a carbon, so it's somewhere here. This carbon here would fit into this environment, carbon bonded to a chlorine. Basically, the environment means that the magnetic moment is slightly different for this carbon to this carbon. And so it's going to require a slightly different amount of energy to flip the spin state round. So it'll absorb a different amount of radio wave energy. So you can see there I've sketched the 2 peaks, and I've just made up some values, some shift values. 22, so that would correspond to this environment here, carbon to carbon environment, so that's this carbon here, and the 50 ppm, so we'll find 50, then it's bang in the middle of this shaded area here, which corresponds to the carbon-chlorine environment. So this is telling us that we've got a carbon bonded to a halogen, and we know that it's a chlorine in this case because we know what the starting molecule was. And so this peak here is for this carbon here. So we'll just summarise where we're at so far. the number of peaks in a carbon-13 NMR spectrum tells you the number of carbon environments. So we had one peak in an ethane spectrum because there's only one environment. We would say those carbons are equivalent. The shift value, remember that's measured in delta, they're using the delta scale. Parts per million are the units, and that tells us the type of environment. And we use the data sheet, which I've got here. The data sheet, we read off the shift value, and that can tell us the type of environment. So if you remember, it was about 20, 22, which correspond to the carbon-to-carbon environment, and about 50, you can see, is within the CCl environment. And so the shift value tells us the environment. So we'll deal with chemical shift now. That's a measure of the amount of energy that the nuclei absorb, the radio wave energy that they absorb to flip their spin states round. If you were carrying out the carbon-13 NMR for ethane, for example, basically you would put your ethane in a solvent. We'll talk about the solvent later. It goes into a tube, very, very thin tube, and you would also put a chemical in that has the acronym TMS, and that stands for tetramethylsilane. So TMS looks like this. We've got a central silicon atom bonded to 4 methyl groups, so that's a tetramethyl, 4 methyls on a silicon atom, so it's called a silane, and this is also present in the tube. So the NMR spectrometer will expose the nuclei to all the different radio wave frequencies, and the nuclei in TMS actually require the most amount of energy to flip their spin states round or to resonate. And so therefore this molecule here gives us our zero value. So it's used as a standard effectively, or a reference peak. So when you look at an NMR spectrum, you sometimes will see a little peak at 0, and that's the TMS peak. So TMS is used as the standard. And then all the other nuclei in the sample require less energy to flip their spin states around, and so we see all the other peaks to the left hand side of the TMS peak. So I've sketched up again there the NMR spectrum, the carbon-13 NMR spectrum for ethane. One environment because the carbons are equivalent. So we see one peak, roughly around 20 parts per million. It's called the delta scale. Delta means difference. So we're measuring the difference between the energy required to resonate the TMS nuclei compared to the nuclei in our sample. And it's such a tiny, tiny difference that it's measured in parts per million. I did say I would mention the solvent, so we'll talk about that now. The sample would be with TMS and it would be dissolved in a solvent. And so the solvent that you choose, you don't want that to give a signal, otherwise it's going to mess up your spectrum. So a typical solvent used in NMR is something called CdCl3, and the D there stands for deuterium, which is the hydrogen 2 isotope. So normally we'd have hydrogen 1, that's replaced with hydrogen 2, so it's given this capital D for a symbol. Well, hydrogen 2 has an even number of nucleons. It's got 1 proton and 1 neutron. Even numbers in the nuclei don't have a spin, and so therefore you wouldn't see a signal from that. The carbon-13 could be present in that, or would be present in that, and apparently that gives a very, very recognizable signal, and the machine just deletes it straight away. So you never see the signal from that anyway. So a good solvent to use for carbon-13 NMR and proton NMR, when we come onto that, is CdCl3. I've just managed to find out from the Royal Society of Chemistry website that the carbon in CdCl3, it gives 3 peaks at 77 ppm, and so if the machine knows that's from CdCl3, this carbon here, it's just going to delete that from the spectrum and you don't see it.